Hello again. So this is the introductory notes to angular kinematics. Okay. So first of all, let's just review our regular kinematics and think about what formulas we have for kinematics. Why don't you take a second, pause the video, and write down all the three main formulas we have for regular kinematics. Okay. So go ahead and write those down. Okay, hopefully without too much trouble you were able to remember that. So I'll go ahead and write those down. So I have delta x equals VIT plus 1/2 AT squared. And I have VF squared equals VI squared plus 2A delta x. And then I also have VF equals VI plus AT. Okay. Now these should all be pretty familiar. At this point, I feel like they should be pretty easy for you. But now what we're going to need to do is take these and make them into angular kinematics formulas. Okay. So let's just take this one and convert it. So I have delta x instead of delta x. I'll have delta theta equals not VI but omega I. Now t time is still just time. So I'll just put t. Plus 1/2, not a, yes, alpha, t squared. And then I have this new formula. So delta theta equals omega I t plus 1/2 alpha t squared. Okay, and everything works the same. It's just now I have angular variables. So let's go ahead and convert this next one. Omega f squared equals omega I squared plus 2 alpha delta theta. And then the last one, omega f equals omega I plus alpha t. Okay? And so these formulas work exactly the same as they did before. Okay? So you should be fairly familiar with this, and we'll do some practice with it a little. We have two other variables we need to talk about. They should be somewhat familiar to you. We have frequency, which is just the number of rotations per second, okay? And that's measured in hertz, okay? And then we have the period, which is just the amount of time for one rotation, okay? And then the relationship between the two is F equals 1 over capital T, or the same thing, T equals 1 over F. This is just flipping the equation around. Okay, so now what we're going to do is we're going to do a practice question, and what I want you to do, or what we're going to do, is we're going to take an old question that hopefully we could solve very easily, and we're going to change it into an angular question and solve it as an angular question. Okay, so what we're really working on doing is transferring our old skills into a new situation, so going from linear land to angular land. Okay, so let's go ahead and slow down so we can solve this question. Okay, after that interruption, we have after more interruptions.
Bus riders and independent walkers, you may be dismissed.
Okay, so a swimmer accelerates at 12.4 meters per second squared for 0.5 seconds. If her final velocity is 9.7 meters per second, what is her initial velocity? So I'm going to rewrite this to make it an angular question. I'm not going to worry about the situation, I just want to give the variables. So I have an angular acceleration of 12.4 radians per second squared for 0.5 seconds. Okay, if the final angular velocity is 9.7 radians per second, what is the initial velocity? Okay, you can see in parentheses we have an answer, so hopefully we can get that same answer. So let's go ahead and use our kinematics methods, and we need to first of all define all of our variables. So angular acceleration, which variable is that? Yes, that is alpha. So alpha equals 12.4 radians second squared. T is still just t equals 0.5. Okay, the final angular velocity, so that will be omega f. So omega f is equal to 9.7 radians per second. And what does the problem ask me for? The initial angular velocity, so omega I. Okay, now which equation has those three things and nothing else? Yes, it will be this last one. So just omega f equals omega I plus alpha t. So omega I is 9.7 equals omega f is 9.7 equals omega I plus 12.4 times 0.5. Okay, and then we just solve for omega I. So I have some questions here, and I just want you to go through those questions and do the same thing I did here. Rewrite it as an angular question, and then go ahead and solve.